Yebo, Jambo, Jebale, Abarigani. This is Dr. Marcelini Dabo. I am a PhD on control systems. I am a consultant engineer in industry and an independent researcher. Okay, so if you want to contact me, the email is here, contact@daboacademy.com. So today I am going to talk to you about always dynamical systems, second order systems, and I will discuss with you how to analyze a dynamical system. So remember that I have talked about dynamical systems of first order and second order in the sense of ordinary differential equations with exclusive approach with time, and I just consider stable systems, meaning that systems with the time constant that is strictly positive. So I have talked about first order systems in the sense of open loop, meaning without the introduction of a controller, and a closed loop strategy in order to control that dynamical system. And for those first order systems, I have talked about the fundamental laws for an autonomous system and also for initial response. Okay. I invite you just to go and check the previous videos. You will have more details. Something which is very important, I have talked about the isoconstant formula, which allow you to compute the time constant of your dynamical system of first order, even when you are not at the 63% of the equilibrium point. I have introduced also an identification criteria of a first order system, which is a ratio between two fixed time responses. Okay. And then I have proposed also for first order systems a table that is showing the temporal performances of our dynamical systems, dynamical first order system, related to the time constant. This is known. For example, time response at 95% is equal to 3 times tau, and then it is equal to 3 divided by omega c, that is a cutoff pulsation, and then it is equal to a given value divided by fc. That given value is equal to 3 divided by 2 pi, okay? And then this multiplied by the inverse of the cutoff frequency. So this was for first order systems. For second order systems, I have shown you that I have introduced, okay, uh, different concepts for second order dynamical systems. Concept of time constant of the surface of time, natural time constant, relative time constant, and only one single time constant for any given second order system. Okay, I have introduced this, and from this, and using another paradigm, I have derived different formulas that I call formulas of Dabo, so my formulas, in order to compute different time responses for different damping ratios of different second order systems that you can have. So this, I have never seen this until today, since I have been studying dynamical systems in the field of control systems. Okay, so this is an innovation. It's a discovery that I am introducing and sharing with you that is done by myself. So let's go now. Today I am going to talk to you about the analysis of a given second order system. So remember that when you have a second order system, if it is autonomous, so I invite you for all these new words that you will be hearing, please refer to previous videos and then you will be able to understand better. If we recall that the system is underdamped, so the expression is here. Okay, this is what we have. You can express the solution like this one. If it is critically damped, the expression is here. If it is overdamped, the expression is here. Okay, and then if you look at these, you will see that, as explained previously, the one single time constant is only defined as this one. Okay, so now from here, what I have done is that with a new vision, a new paradigm, I have considered that any given dynamical system of, might it be of first or second order, will reach a given percentage of the output of the a certain percentage of the output according to the initial condition, for example, in the case of an autonomous system, at a given time, and that time is equal to the multiple of its time constant. Okay, and this yields to this result that is linking the percentage to a certain given multiple alpha of the defined time constant in the sense of Dabo, meaning in the sense of what I have introduced. Okay, so you have it for the damping ratio less than 1, a damping ratio equal to 1, a damping ratio greater than 1. And then from here, let me now show you some examples. So in the French version of this video, I have treated this one, okay, I have treated this second one, and I have treated this third one. So I'll try to treat this one, okay, this second one, and this third one. If we have all the cases that we want to have, meaning having a critically damped, overdamped, underdamped on these three, I will be able to show you. So I will be okay. If not, I will come back to some of them in order to show you that this is critical. And then, for example, this is an aperiodic response or an overdamped system, such that you will be able to see how I derive and compute the different time responses even before getting them on the simulation. And then after, so next videos, of course, I will try to present you something else, okay? So these are some functions that you have here, taken from the book of Professor Godfrey Onwubulu. And then these are examples that you also can treat based on the examples that I will be showing you. It is always extract from the same book. If you just want to have different static gain, okay, what you can do is just you change this value, because normally here, as this expression is given, here is omega n squared that you have here, and then b is equal to 1, and then you repeat the omega n squared, so b equals 1. That is the static gain, finally, of your second order system. So you can see it directly from here. So now all these elements and all these way of analyzing, of course, these formulas that you see and different as tables are, of course, resumed in this book. This is the French version and the English version is coming, okay? So this is a bookmark that will come with the book. So let's go back to the different examples that I want to show you how from a transfer function. So just a comment. Don't worry about these transfer functions because as told at the beginning, I am using only time approach for these calculations, and it remains, of course. But these transfer functions that you can see here are, as you know, only the equivalent of this dynamical, of this ordinary differential equation with all the initial conditions put at 0. Okay. All right. So now this is said, and then so now let's go. Let's go now to do some simulations. Um, just plug my computer quickly. Okay, so now computer is plugged, and then let's go to check the software. Here is always the same. So if you want to understand details about this simulation, please go back and check the previous videos. It will be very clear for you. So now if we start for, if we start with this one, number C, we have 16 over 16, meaning that the static gain is equal to 1, okay? Now here we have 10. What we will be having is that this 10 is equal to 2c omega n, and this 16 is equal to omega n squared. And 4 times 4 is 16. And then we will use this in order to derive the omega n, okay? So now let's go. Let's go to check that. As I said, B is equal to 1. Okay, so the static gain is equal to 1. Now let's go to see what is the corresponding C. Let me do it this way. If you check the corresponding C, okay, you have 10, and then after the square root is 16. So this is the value of our damping ratio, 1.25. So you see that this is an overdamped system. How to compute the time response of this value of this dynamical system directly without any simulations to do? I can tell you, according to my definitions that I have introduced, how to compute it. This is what we are going to see. So now this is it. What about the omega n of our first system? We say that this omega n is equal to the square root of 16, right? And then this gives us 4, okay? So now what about the time responses that we want to compute, and how will we be computing them? Recall that I have introduced in the first time of control for control system or motor control engineering that any given second order system has only one time constant that is equal to tau s, equal to the double of the relative time constant that is equal to 1 over xi omega n. Okay? And then, so from here, now let's go. What we are going to use, we are interested on knowing what is the value of the coefficient, the multiple alpha that will multiply the time constant of our second order system. This is what we need first to know. So to do so, we take this. What we are going to use as formula here is this one, because xc is greater than 1, we will use this function that is related, that is allowing us to compute the percentage of the initial condition, of course, according the percentage of the output according to the initial condition, and it is a function of alpha, that is a multiple that I was talking about, and you can see the C is inside. So now let's go to do this computation. We will trace the graph, okay, and then check on the graph which value of alpha will be corresponding to a given percentage at which we want to compute the time response, right? Let's go now. So let's go to find what we want to do. Baba, oh. If you want to sing with me, you can. Baba, oh, oh, Baba, oh, Baba, oh. Okay, so now we have here 1.25, that is xc. And then the omega n is now 4, but we can write the square root of 16. And then from here, we are going to, we will not simulate. This, I will come back to this line, okay? 153 later. Let's go to first plot our first function gamma, right? It is an overdamped, as I was saying. So if we put here 1.25, this is what we have here. We will be computing and plotting this figure. Evaluate. Okay, and then from here, what we are going to have, I invite you to check very very deeply what I am doing. So here you have alpha on the abscissa axis, and the ordinate you have y, that is a gamma, as a percentage. Let's now fix something here. Okay, and what we want to compute is a time response, let's say, at, let's say 20.7, okay? Let's say 20.7, this point, okay? So the corresponding alpha is equal to 4.6544. So if you want to compute the time response at 20 something, you will check that you have the alpha times, so alpha is here, 4.6544 divided by xi. The xi is equal to 1.25, as we said, multiplied by the square root of 16, that is 4, okay? And then this yields to this result, okay? So let's go and simulate and see what we will be having at this time response. Let's go. Or we can do it also, because this is at 20%. Let's go do it at 10% and then check what is happening. What is the value of the time response that we will be having? Let's go, let's go, let's go, let's go. Let's go. Baba, oh, Baba, I like this song. What about you? Okay, so here what we have the time, given time response is here. Let's say we have it at 10 something. Okay, this is 10%. Okay, so this 10%, we will be checking. The values that we have here is 6.4754, right? And then this is the time response that we are supposed to have. So just to come back here at the time response at 20 and check what is the reality. What is the reality there? Because I just want to have something more precise, or to take the percentage exactly at 20%. This is why I'm coming back to this value. Okay. Okay. So now I think this one is the best. And then if I correct it, the time response at 20, the corresponding values that you have here is 4.7407, okay? 4.7407 divided by same. This is the time response that we should have at 20%, okay, of the initial condition. We have at 10% of the initial condition. Let's go to 5% and then stop there. And then for these three time responses, we're going to check what we have. Let's go. 5%, I say. Okay, if we try, so we have this. And then the time response at 5% for an autonomous system will be equal to, it will give us 8.2085. And this is our time response. Okay, so we compute it at 10%, we compute at 20%, and then at 5%. These are the values that we are supposed to have for our system. Okay, we don't yet simulate. Okay, so let's go now and check and simulate. I said line 153. What about 153? It is here. Okay, so now we are going to compute this. Okay, once we compute this, we launch the simulation. What I'm having here, I can take just an autonomous system, okay? Because I don't want a step, I just want an autonomous system. And then if I do so, I will not be clearing these computed values of time response in order to be able to compare them. Let's go. Just to check the damping ratio is okay, the omega n is okay. All right, so omega n is here. I mean the 4, not the parenthesis. Of course, you have understood. So here, once we do this, we plot our response. Coming very soon. And then from here, let's go and find what we have computed. So the time response at 5, as I said, is equal to this. Okay, 1.6417. Let's go and check if it is true or not. 5%. 5%. Look at this, 1.6417, 1.6417. It is exactly the same, okay? These are the result of simulation from Simulink. These are the theoretical calculations that I have shown you how to derive it, okay? And then you see that I have, it's not, it is a periodic response. It is overdamped response system. And honestly, in the different books that I have seen until today, I have never seen the way to compute these values and to see what are the performances, the temporal performances that I am supposed to have. And then, of course, as I tell you, next videos will be I will present in next videos how to do some specific stuffs that can be very helpful for you, according to my paradigm, of course, and my vision. So TR at 5% is here. If we go to check the TR at 10%, we are supposed to have this value, 1.22951. For 10%, where are we? Here. So now let's go. And then, so here you are, we have 1.2951. Look at this. The response is correct. And then for the 20, okay, I guess I have computed this value. Yes. 0.9481. Let's go for 20%. 20%, where are you? Where are you? 0.9482. Okay, you have it here. You have it here. So we can notice that the time response that we wanted to compute is this one. What does it mean? It means that you can have a dynamical system, and then even before you do the first simulation to check what is the corresponding time response, etc., it is absolutely possible to compute the time response of the dynamical system of second order, even if it is overdamped. Okay? So now this is done. Let's go and consider a second example here. So I am going to take this one. I told you this one, this one. So now let's check. Let's study this case. So for this first, we had an overdamped. Let's check for this one, 15, 5, and 15. So the omega, how do we compute the xi first? The omega here is, you see, omega n square is here. So the omega n is a square root, of course, of 15. So the xi of model number 2, I put here number 2, here we have 5, and then here we have 15. This is the corresponding damping ratio of our system. So before we go further, what we do, at this step, we check also first the omega n, the corresponding omega n. We say it belongs to model number 2, and then the square root of 15. Okay, this is a given value. This is omega n that we're supposed to have. If I check again my system, 15, 5, 15. So 15 for the omega n and 5 for the Xi, corresponding damping ratio. 5 here, omega n square here. Okay, and then this is what we have. So now let's go and then check, look at the different values of the multiple that is alpha. The graph is here. We can put here the value of the damping ratio. Here, the omega n is a square root of 15. Okay, and then once you have this, the static gain is equal to 1. Let's go for this. This will give us the graph, okay? But what we want is just to compute first the time response, okay? You can see the value of the damping ratio is very particular. Look at this value is particular. And then for this particular value that I have, I will be able, according to my formulas that I have introduced in control systems, I will be able to compute this very easily. Let's go. If I take so if I take this value here, this is for an underdamped system. We will compute the gamma function. So it means that we will go and check first this function, okay, the percentage related to alpha and the Xi. So this is why we fix the Xi that we want. It is here. And we will just start for this, just take this first value. So let's check the first value that we have here. So this is what we have, okay? And then from there, we are going to check the different time responses. If you check it here, let's say at 5%, or let's say at any given percentage that you want. For example, if I consider this percentage, how will I be deriving the time response at 35? Okay, 0. Okay, 289. This is the time response that at this percentage that I'm looking for. Okay, and then it is equal to, never forget that it is always alpha divided by Xi times omega n. Okay, so the alpha is here, 1.1146. 1.1146 divided by Xi mod 2 times its own omega n 2. And then we celebrate, this is the time response at this percentage. So now, let's go and simulate and then check if we are going to have at this percentage the same time response that we have computed theoretically. Here is what we have. Our Xi is here. Our omega n is here. Okay, and then if you just check the omega n2, okay, you can see this is a square root of 15 as it is written here. Right, so now let's go. And here I will be having an autonomous response of my system. Let's go, and then we are going to plot very soon a new figure, evaluate. this is what we have. So let's go and check at this percentage where we are now, meaning at 0 0.35, 0 0.35, 35, 0. Okay. I'm sorry. Let's go 0 0.35, 0 to here is 0 0.3. If we do this, what we are having here is this value 0 0.4458. And then if you take the time that we have computed earlier, time at 0 0.35, is it correct? No. At 35, is it correct? Ah, maybe I have forgotten something like this. Okay, no problem. Let me just go back here and take this value. Okay, so what we have here, you can see it is 0 0.4458. 0 0.4458. This is the time response that we have computed from here. So if you don't want the time response here, and then you want it, for example, let's say here, okay, or let's say at the peak value that you have here, okay, I will be not, I mean, this is the time response. You can see it, okay? If we position ourselves to see the alpha, the corresponding alpha that we have here, okay? Let's just go back a bit. No. No, 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 no. Let me push it this way. Okay, this way. So 20, no, this way. 25, 19. 25, 25, 19. Let's say this one is okay. Okay, so this is the alpha that we should use to compute the time response. Let's go for the alpha. If I say I clean everything and then I take the time response at this percentage that you have here, I will just call it X. At this percentage, the corresponding alpha is on the magenta curve that you have here is 2.6761. 2.6761. If you say okay, so you have the time response that is equal to this. 1.07. This is the time response that we are supposed to have. Okay, and we have 1.05. It is not far. Okay, if I consider, because here what we have 0 0.0702519, and here is a bit different. Okay, if I consider, for example, the response, let's say at 10%, just to show you what I will be having. Let's put it at 10%. 10%. So the alpha, the corresponding alpha of the time response at 10%, okay, is equal to 1.5945. 1.5945. This is it. I say, okay, this is the time response that I have. If I come to check here, what I will be having 10%. You can see that here I have 0.6378. That is exactly the time response that I have computed theoretically. So this is what I wanted to share with you. Another point, that is, let me consider this exercise. So we have studied this one, we have studied this one. So now let's try to study this last one, where you have the here. So if I develop, I have s squared, and then I have 7s, and then I have 12 here. Okay, so 5 over 12. And the static gain is equal to 5 over 12 for this function. So b is equal to 5 over 12. B2 should be equal to this value, okay? But what about the Xi? This is what we are going to see. Sorry. So we say Xi and then the Xi mod number 3. We have 7. This 7 is divided by 2 times the square root of 12 because 3 times 4 is 12. And then this is the damping ratio that we have. Specific damping ratio, very smoothly greater than 1, and then very little, okay, it is greater than 1 in a given subtlety. And then this omega n that we have here, we say that it should be equal to square root of 12. Okay? Square root of 12. And then, okay, this is what you have seen. Let me show you. It is here. If you develop this expression, 3 times 4 is 12. Okay, so the omega n carry, corresponding omega n square is given here. Go back to the computation. And then here, as the Xi is greater than this, so the omega n3, let's go for omega. Omega n3 is equal to square root of 12. And this is this value. Okay, so now we are going to plot again. We are going to check the corresponding alphas. Corresponding alpha to these damping ratios that are greater than 1. So the system is overdamped. We have this one that we are going to put here, right? And then from here, let's check a figure. Do I have a figure? Open the figure here. Yes. This is a new one, so I have to close these figures. So you see that the curve of the percentage is following exactly the curve of the system, okay, the response of the system. So I close these two, and then after I go for this one, evaluate. So if I evaluate this one and say here that I have a CLC, what I will be having there is that let's just consider this at 10%, okay? And then we try to find a more precise value. 10%, where are you? Okay, so let's say that at 10% of response of the autonomous system, what we have is a time response at 10 is equal to, here you have the Xi number 3, the omega n number 3, and then here the alpha that I'm having is equal to 3.9834, right? Go, here you compute, and then let's go for simulation for only this 10%. Let's go for it. What we are going to have, we are supposed to have something from here, okay? And then now we go, and you see the value of the time response that we are supposed to have. Where is it? If I do this, I am supposed to have a given time response that I have just computed that is equal to this value. Okay? So now let's go and check here. At 10%, what we have. 10%, what we have. Let's say that it's okay here. 1.138, 1.138. So guys, I think that this is clear. It is the demonstration of the discoveries I have made to analyze any given dynamical system. And I forget to tell you, if you have this C, you see that it is greater than 1, to write the solution of this expression, okay, of this expression in time, okay, you just come here, you say that C is greater than 1, and then you take this expression and write it for what? For an autonomous system of second order, okay? And then you replace the given values that you have computed, the parameters omega n, xc, etc. If you want the expression for an initial response, meaning that you have the static gain that is 1, and then you have also, what else? The initial condition is 0, okay? Static gain is equal to 1. The amplitude of your step response is equal to 1. So now the response, initial response will be equal to 1 minus all these expressions that you have here. Okay. So thank you for watching. Please prepare yourself to order this book in its English version. It is coming very soon. French version also are coming very soon, and I will be very happy to share with you the links very soon. So please enjoy, like, subscribe on my channel, and share these jobs, these discoveries in control systems. To tell you, I am an independent researcher. I just do this because I like it. Okay, it's my field is control systems. Very happy to share these results with you. I hope that it will help you to develop many other things. So again, thank you for watching. Again, thank you for staying tuned, and like, share, subscribe. Saumbona Gakulu, Dilen Jajaf Al Mubahabah, Dr. Marcelin Dabo, African from West Africa, Senegal. See you soon.